Okay, delivering pizzas. A certain car model has a mean gas mileage. So this is for the whole car model. Population mean is 29 miles per gallon. And that population standard deviation is 5 miles per gallon. A pizza delivery company buys 47 of these cars. So the number of cars they bought, 47. What is the probability that the average mileage of the fleet? So, different, right? The last question asks, what's the probability that one crocodile is greater than 12 feet? This is asking you about the average mileage of the entire fleet. So this is asking you about X bar. Not one particular X, but the average of all the X's. What's the probability that that is between 27.9 and 29.3? Okay. So because we're being asked about the average, right? We're asked about the probability that the average is less than this, greater than that, or whatever. This is going to be a central limit theorem problem. One thing that gives that away is that we're asked about the average. We're not asked about one particular value, one particular car. We're asked about the average of the entire fleet. The other giveaway is that we're given this n. We're given this n equals 47. Why does that matter? Well, if I go to my formula sheet, see the central limit theorem formula? C equals x bar minus the population mean divided by sigma over the square root of n. See how that x bar and n are in there? That kind of gives you a clue as to what's coming. Because we have to standardize these values. Same idea, right? I can draw my little picture if I need to. My mean here is 29, right in the middle. And we want to know what's the probability that the average is between 27.9, let's say that's about there, and 29.3 is right up there. So we want in between these two values. So the kind of method that we'll be using is we'll be converting these to z values, converting these x values to z values, and then we'll go to the table for this one. Table gives us to the left. We'll go to the table for this one. Table gives us to the left. And then if we subtract those two values, we'll get that area in the middle that we're interested in. So we'll be using the central limit theorem formula twice. And I have everything listed there. X bar. The first one we'll use is 27.9 minus my mean of 29 divided by 5 over the square root of 47. I'm going to put this all into the calculator. Check out how I do it. Numerator in parenthesis, 27.9 minus 29 divided by my denominator in parenthesis, 5 divided by square root of 47, close both of them, negative 1.51, I'm going to round properly this time, negative 1.51, and I'll do the other one at the same time. This x value is 29.3, x bar value is 29.3, minus 29 over 5, the square root of 47. I'm just going to hit second, enter, to re-input that first one, and then just change that to 29.3. There we go. 0.41. So this question is really asking now, if I convert it to standardized normal values, what's the probability that z is in between 1.51 and 0.41? So I'm going to go to the table for negative 1.51, go to the table for 0.41 and subtract them. So this is going to be equal to, use a different color there, negative 1.51. Let's see, negative 1.50, negative 1.51, 0.0655, negative 1.51, 0.0655. So this area here is 0.0655. That's going to be the smaller one, so that's what I'll be subtracting. And 0.41, 0.41, 0.41 is 0.65, 0.41 is 0.6591. So I'm subtracting these two, 0.6591 minus 0.0655, 0.5936. That's the area that we're looking for, right in the middle. So this is the format for in between these two values. Find the two separate z values, go to the table, find the areas under the curve between those two, subtract them,